Hello, this is Professor Zaman. Today we will discuss about matter, charge, and how eventually we get electricity. So today's discussion will be our first video in the series of DC circuits for electrical engineering students. But this discussion should be useful to anybody who wants to learn about charge and electricity. It doesn't have to be an electrical engineering student. Whatever we are going to discuss today is something you have already learned probably in your high school. But still it should be a good refresher and something to know if you haven't learned it before. So first we will talk about what is matter. Everything we see in our life, for example, our clothes, this pencil or board, you can break them apart into very small particles. The smallest particle you can get to of any matter, when you cannot break it anymore, is called a molecule. So if I write it down on the board, a matter, so any matter can be broken apart, and the smallest particle you can get to, we call a molecule. An example, let's take water. If you break apart water, and the smallest thing you can get to of water is called a molecule, and the symbol for a water molecule is H2O. You might have learned this in your chemistry class or some other ways. So what is H2O? H2O is a molecule. It is made of 3 atoms. Which are those? Those are 2 hydrogen atoms and 1 oxygen atom. So if we break H2O into 2 hydrogen atoms and 1 oxygen atom, this will no longer be water. It will lose the property of water. So that's the third level. So let's call this atom. Now there are other materials which are directly made of atoms. There are no molecules. For example, copper, which is very important material for electrical engineering, because we use copper every day, everywhere for current conduction. You take any wire inside, underneath that plastic coating, you will see copper wires, because copper is a very good conductor of electricity. So if you take copper, let me write it down here. Copper actually is made of directly atoms. And the symbol for copper in chemistry or science is Cu. What you have learned here, eventually any material can be broken down into its atomic level components. For copper, it's just copper. For water, let me write it. For water, there are 3 atoms, 2 hydrogen atoms and 1 oxygen atom. You might ask, why were we discussing this in a DC circuits or in the context of charge? Because actually everything we use in our lives are made of these atoms, but within the atoms there are charges that you don't see normally, because atoms are normally charge neutral. But you can make them charged by changing something or removing something from the atoms. So that's where we're going actually with this discussion. So every material is made of atoms, but the atoms are charge neutral. There is no charge. You can make them charged by taking something out of them, which we call electrons. Let's look at the structure of materials. So we'll discuss more about copper now than this part, because copper is a very important material to understand electricity, because we use it so much in current conduction. So from outside, a copper wire looks like solid, it's a strong thing. But actually, materials are mostly hollow inside. Even though it shows or it looks like a strong material, hard material, but inside there are a lot of hollow space. So let's look at the structure of a copper substance. Let's try to draw a copper wire. So a copper wire is this is a copper wire, round shape. Okay, made of copper atoms. Copper atoms. This is a copper wire. But if you look very inside the material with a microscope, a very powerful microscope, you'll see. So this is the top surface. So this is the same top surface here, and each of these atoms actually is like a circle. Okay, there is a circle. There is a circle. There is a circle. These are atoms. So each atom is made of a center we call nucleus, and also there are outside things which rotates around the nucleus, which are called electrons. The nucleus is made of protons and neutrons. But the electrons that are spinning around, they are outside. So they are rotating in different orbits around it. So you see, it's mostly hollow. Only the center nucleus is a strong thing, but outside it's mostly hollow space. But there are forces between them. You cannot really collapse them into a single smallest entity. So you cannot push them in, make them smaller. So from outside, copper wire is a strong thing, but actually it's mostly hollow thing. Let's continue with the discussion with copper. So how does the copper atom look? So let me draw that here. This is the nucleus. It has protons and neutrons, and the outside electrons are rotating in different orbits like this. I didn't mention neutrons have no charge, but protons actually have charge, and electrons also have charge. But the nature of charge is protons have positive charges, electrons have negative charges, and they are equal in amount. The amount of charge an electron has is same as the amount of charge, positive charge, a proton has. So just their signs are different, opposite, but the amount of charge is same for electron or a proton. So that's why we see an atom is charge neutral by default, because there are equal number of electrons and equal number of protons. If there are 4 electrons, there will be 4 protons. So if you sum them up, you have 0 charge, because equal negative charge and equal positive charges. So let's look at the structure a little more. So we have the protons here, plus charges, and we have the electrons rotating in the different orbits. It's like a planetary system. This is the sun, all the planets are moving around it. So this is a two-dimensional picture. You have to visualize as a three-dimensional spherical picture. So some electrons are going this way, some are going this way. They're not like in a plane. They're actually in a 3D spherical shape. Now, how many electrons are there in different orbits depends on certain physical law. Nature has created them. So, for a copper atom, there are 29 protons and there are 29 electrons. I write minus sign meaning the electron. Out of these 29 electrons, only one electron is on the outermost orbit or shell. So this has very loose connection with the nucleus, which has protons and neutrons. That means its attraction is very low. Okay, and it spins at a high speed. It has high energy, and it has loose connection. Its negative charge the charge of electron is negative. So in its negative charge, there are positive charges in the nucleus, but because of the distance, their bonding is very weak. There is force of attraction is very weak. We all know that negative charge and positive charge attract each other, but because of the distance, the force of attraction is very weak. So it's possible you can take this electron out of the atom and it becomes a free electron. So if that happens, for example, from this copper atom, electron comes out. So that means now this copper atom has 29 protons but only 28 electrons. So as a result, this copper atom is no longer neutral. It has a net positive charge. So whenever an atom loses an electron or two electrons, it will become charged. In this case, it has a net positive charge, and we call this process ionization. Whenever the electron comes out of an atom, it creates a positive ion, in this case a positive copper ion, and this negative charge electron is called free electron. Okay, so this will be called free electron. Why are we calling this free electron? Because now it is free, it can move. You see the gaps here? This is a 2D view. In a 3D view, there will be gaps going in this direction or going down or going to the left. Through these gaps, these electrons can move, and that is the source of electricity. Okay, so we have free electrons in copper, and by the way, for copper it's easy to get the electron out, so that's why copper is a good conductor. But you cannot do that for all materials. For example, for wood or plastic, you will not be able to get the electron out easily. That's why they are not good conductors. Okay, but we are limiting our discussion here with good conductive materials like copper. There are silver, gold, those are also good conductive materials. Since copper is the mostly used material for current conduction, we are limiting our discussion to copper here. But this discussion in principle will apply to other conductive materials as well. So we have come to a point we can talk about electricity. So whenever at room temperature, usually there are a lot of free electrons in a copper material, and they don't stay still. They keep moving constantly, this direction, that direction, this direction. There are many electrons, but in general there is no net movement. If one electron is going this way, other electron is going probably this way, so net charge movement is zero. So there is no electricity. But if you apply an electrical force, we call that voltage, then suppose we apply a positive voltage on this side, okay? This electron will tend to move this way. So in that case, what will happen? Most electrons will try to move this way because of the attraction between electron and positive charges. Still, there will be some will move probably this way or in other directions, but the net movement of electrons will be in this way, and that is what is electricity, movement of charge. To summarize again, I will say all materials are made of molecules or atoms, but even if there are molecules, the molecules can be even broken apart into atoms. So ultimately there are atoms at the smallest level of any material, and those atoms, in some cases for conductive materials like copper, some of them can be taken out of the atom or brought out of the atom. You can say they can be made free by external forces. For example, temperature, I didn't mention it before. The energy of an electron increases whenever you have temperature increases. Suppose we put it in sun or if the room has good high temperature, or normally even at room temperature, it can gain energy to come out of the atom. And those electrons normally do not generate any electricity, but if you apply a voltage, suppose positive on this side and negative on this side, these electrons in general will try to move this way, and that will cause current. So when electrons are moving this way, so there will be a current flowing this way. Why? Because by convention we say, whenever positive charges move, the direction of the positive charges movement is the direction of the current. But here you see, actually there is no positive charges that are moving. Positive charges are in the copper ion, which are static. They cannot move. They are fixed in this structure. By the way, this structure, the atomic structure has a name actually. You might have heard it. It's called lattice. Okay, this structure is called lattice. This atomic structure. So the copper ions are fixed in the lattice. They cannot move. Only the free electrons can move. And when you are applying a voltage, they are moving this way. But electrons have negative charge, so that is not the direction of the current. In this case, we will have current this way. So again, to make it clear, the thing that is moving is only electrons. The thing that are moving are only electrons. But we will call the current is flowing this way. Sometimes it becomes a little confusing to beginners. They think, okay, if something is moving this way, that is the direction. But for current, it is always the opposite of the electron flow direction is the current flow direction. Now, I should also add this phenomena or this discussion only for conductors, but there are other types of materials where you can have sometimes positive charge movement. We have three classes of materials. This is conductor, and there are semiconductor. That means they are half conductor, and there are insulators. So conductors like copper, there are a lot of free electrons who can move. In a semiconductor, there are very few free electrons. But an interesting property of semiconductors are that you can have positive charges movement in semiconductors, which is very important for electronics or making integrated circuit chips, IC chips. So even though they are not good conductor, they are very useful because we make like silicon is an example of a semiconductor. We use that extensively to make IC chips. And insulators obviously do not have any free electrons. It's very hard to get the electrons out of the atom. There are almost no free electrons, so they do not conduct current. But they are also useful. For example, if you didn't have insulator like plastic that covers the copper wire, if you touch a copper wire, if there is current, you get a shock. But because of the insulator, it's protecting you. You are not getting the shock. So all of these materials have their unique properties and they are all useful. But for current conduction, we have to remember that we use conductive materials or conductors. And the reason current is created is because whenever electrons get free, because of external effects like temperature or sunlight, they can move and that causes current. And generally, there is no net movement of electrons in one direction. Even though they are moving, there is no current. But when we apply a voltage, they start moving in a certain direction and that causes a current flow in the other direction. So that's it for today. Please listen to our next video where we will discuss how much current we get for applying certain amount of voltage. Thank you.